Oh, just check. So, some announcements. Test grades will be up tonight. They're basically graded. I just need to run through the, sum up the grades and look through the numbers. So they'll be up by tonight. Should be shortly after class in all likelihood. And we're going to start chapter 9 on the mechanics of biological materials. So we talked about general mechanics, how things move and work. Now we're going to move on to talking about how various materials function and material properties. And we're going to focus on the materials of the body. So we'll look at stress and strain in the body, where stress is related to force applied to a material, and strain is related to how much it changes shape when that force is applied. So we'll define mechanical stress, we'll define strain, we'll define tension, as in tensile strain and tensile stress. We'll define compression, compressive strain and compressive stress, and we'll define shear strain and shear stress. Those are the 3 types of stress and strain that can occur on a material, and often materials will have different properties with regards to those 3 types of stress. We'll identify and describe bending loads and how they combine multiple types of stress. They combine tension and compression and can also combine shear. We'll describe the stress patterns that develop under bending loads. We'll identify and describe torsion loads, and we'll describe the general stress-strain relationship for an elastic material. We'll go over what elastic's modulus or Young's modulus is, and we'll describe elastic and plastic behavior. We'll look at the various descriptors of material strength, which are yield strength, ultimate strength, and failure strength, the 3 different ways you can define 3 different strengths something could have. We'll define the concepts of stiff, ductile, brittle, and pliant. We'll go over what toughness is. We'll look at the material properties of bones. We'll look at the material properties of tendons and ligaments. And we'll just look at the material properties of muscles. The 3 major types of material in the body, which are muscle, connective tissue, and bone. And these slides have been slightly updated. I added some extra pictures. They've been updated on Blackboard. So, external forces impose loads. External forces on a body will affect your motion, and they also load a body and affect internal structures. So when an external force is applied to the body, you have some load or force on the internal structures of the body. These are things like cartilage, tendons, ligaments, bones, and muscle. These are the internal structures that are affected by the forces from outside. And the mechanical response of structures, how structures respond to these external loads, is related to injury. Because when parts of your body are stressed beyond their limits, you get injuries. So when we look at the mechanics of materials, we stop considering objects as rigid bodies. We consider any segment to be a deformable body, which means it can change shape or size. And external forces that are imposed on some portion, segment, or body are resisted by the internal forces of the body, and this causes the deformation of the body. The external applied load is the stress. Stress is defined as in terms of force over cross-sectional area. So that's stress. So it will be in units of pascals, generally, because it's a pressure. And the deformation caused is the strain. And the deformation is defined, the strain is the change in size of the object over the original size of the object, the fractional change in size of the object. So mechanical stress is how an applied force is distributed over a body that it acts on. Mathematically, stress is force over cross-sectional area of the internal surface. So that's if you have like a rod, and you have some force applied downwards on it, the area in question would be a slice through the rod. So it would be this slice through the rod. That would be the area in question. So that's the cross-sectional area of the internal surface. So it's newtons divided by area, meters squared. The units are Newton per meter squared or pascals. Because meters squared is a very large area. Pascal is a small unit. Generally, these will be pretty large values. So Q, keto, and so stress is the applied force over the cross-sectional area. So when we talk about the stress on an object, that's what we're talking about. And that stress, when you apply a force on an object, it will deform the object, and that deformation is measured with the strain. So let's see if I have something, a rubber band. So if you think about a rubber band, consider stretching a stretched rubber band. Let's see if I have a rubber band around here. I don't know if I have any usable room as an example. So we have a thing, we're stretching it. It's in equilibrium, so the net force is 0. The pulling force from my left hand is equal to the pulling force from my right hand. And if we cut a slice through this rubber band, each half is no longer in equilibrium unless forces pull in the directions opposite to the pulling force to the left end and the pulling force to the right end. And so the force that needs to be at each end is the internal force, and you can calculate that. In general, if you have a nice even thing, it's just going to be the same as the pulling force. So here, for example, we have a rubber band. We sort of cut a slice through it. We're applying some force. There needs to be some internal force here that is applying that force. And we distribute that force over that area of the slice. Okay, so this image got fast up. Let's see if it's any better in this book. Go ahead. Or is it equally more fucking important? I can't handle the pictures in this picture. No, it's better in your book. So figure 9.1 in your book. I think I might be able to replace this. Unless, let me get figure 9.1 in here. And I mean, I already updated these slides, but chapter 9. Nope. I don't have a digital copy of the good one, so you'll have to look in your book. I don't know why the image in the image bank is all totally messed up, but like this clearly got corrupted somehow. Just by looking at it, you can like the thing. This should be being cut in half in the middle, and it's really messed up. So let's not look at that picture anymore. But the idea is that you have a rubber band or some object. You can think about slicing it in half in the middle. And in the middle, the force, for the forces to all work out for each half, there has to be internal forces pulling inside the object. And those are the forces that cause stress. And you distribute that force over the cross-sectional area, and that is the stress. You have a slice that you cut through, and there's so much force that's internal in that slice, and that's the stress. For this class, it's generally going to be the same as whatever the external force is. So we'll just show that Jada. So in general, stress, force over cross-sectional area. Unit is newtons per square meter, which is pascals. And often it's going to be a big number because a square meter is a very large area. So a pascal is a very small unit. So you'll see lots of megapascals and gigapascals in the book. So the force is the result of many intermolecular bond forces across that whole imaginary cup plane. That's the force. And the cross-sectional area of the imaginary of the plane is the area over which the internal force is applied. That's the A, the area in the stress equation. So that's stress. It's written with lowercase sigma. There are three principal types of stress, depending on the type of force applied. They are tension, pulling, the primary stress you have on like a rope. So this rope is, I'm pulling on this with tension. Ropes are strong in tension, but they're weak in compression, which is pushing together. Other stuff like, I don't know, a stack of paper is strong in compression, but really weak in tension. Got no tensile forces, but it compresses just fine. And then lastly, there is shear. Shear is sort of side-to-side sliding stress. So that's a stress that where the force, instead of being perpendicular to the plane that cuts through, is parallel to it. So, if I had a cylinder of some sort, this, I'm pulling on it, it's tension. If I'm pushing it in, it's compression. With shear, I would be moving one side up and the other side down. And external forces act perpendicular. Axial stress are when external forces act perpendicular or normal to the analysis plane. They're also called normal or longitudinal stresses. These are tension and compression. And a uniaxial load is an external, when the external forces are all collinear. They're all lined up. So tensile stress is an axial or a normal stress. It occurs at the analysis plane as a result of the force or load pulling the molecules apart. And tension causes a body to deform by stretching. When you apply tension to a body, it will stretch. So, for example, for a bone, the cross-sectional area depends on the plane of analysis. And in the areas with a larger cross-sectional area, you have lower stress. With a smaller cross-sectional area, you have higher stress. So if you have a bone here at this slice, the force, this is a humerus loaded tension, the force here, the stress here is going to be higher than the stress, say, up here, where the cross-sectional area is larger, where the bone is thicker. So the stress is going to be biggest at the skinniest point, the smallest cross-sectional area. So here's a simple tensile stress calculation. Your cross-sectional area is 1 square centimeter. That's 0.0001 square meter. Yeah, the areas are going to be small numbers. A square meter is a very big area. Yeah, like this. The tensile force applied is 700,000 newtons. That's a lot of force, but definitely possible. And the maximum tensile stress is going to be 70,000 newtons divided by 0.001 square meters, or 7 billion Pascal, or 7 gigapascals. So lots of mega and gigapascals you'll encounter when we talk about stresses. Now, compression is kind of the opposite of tension. Tension is stretching, compression is squishing. It's also an axial or normal stress. It occurs at the analysis plane as a result of a load squeezing the molecules together at that plane. And compression causes the body to deform by shortening. It gets shorter. Again, for bone, cross-sectional area depends on the plane of analysis. Larger cross-sectional area, lower stress. Smaller cross-sectional area, higher stress. So here is a humerus loaded in compression. The first was tension, you're hanging from it. Here is compression. And again, biggest stress is going to happen at the skinniest point. The force is squeezing together the bone, and it will distort the bone by shortening it. Bones, for example, are strongest in compression. Like lots of things, you know, a lot of things out there are either strong, very strong in one compression, but not tension, or vice versa. Some things are strong in both. And then shear is a transverse stress, not a normal stress. This is acts parallel to the analysis plane and is a result of non-collinear forces sliding molecules into that plane. So if you have forces that are not collinear, not lined up, you can get shear stresses. So here, if if right hand pushes forward and my left hand pulls back, I'm going to get a shear stress in this. Shear stress is represented with tau. And this is, the force of shear over the area. And shear causes a body to deform by skewing. A good example of that is sort of if you take a deck of cards and you push on it, the top of it, the whole thing sort of skews over. The top slides over, the bottom stays in place. I could maybe do it with a pile of paper. But that's what skewing is. I guess I could do it with a pile of calculators here, just to demonstrate. So if I apply a shear stress to this, it will skew like this. Again, the easiest way to think about skewing is to think about lots of thin, flat things on top of each other. So here is an example of shear stress in a pencil. This side's being pushed up, this side's being pushed down, and there's an internal shear stress at the divide. That's how you can think about it. There has to be some internal force to counteract this external force. So it's the internal force that is the shear, that causes the shear stress. And here, this is like a piece of paper. A piece of paper is strong in tension, weak in compression, and relatively weak in shear. That's what you do to tear things, is you shear them. Yes, they're called shears. The force that shears apply is shear. So there's one side goes down, the other side goes up, you have a shear force. So here is what happens with tension, compression, and shear. Tension, the object stretches, it gets longer. Compression, the object swooshes, it gets smaller, shortens. And shear, the object will skew. So, various sorts of stresses can cause various sorts of injuries. Tensions. You can get a sprain or a rupture of a ligament and tendon. You can get a strain or a tear of muscle and cartilage. Those are tension injuries. Compression injuries, bruises of soft tissue, crushing fractures of bones. Shear injuries are things like a blister on your skin or a dislocation of a joint. Bone breaks tend to actually be more complicated forces than just one. But these are some example injuries of the associated stress. Now, when external forces are not all along one axis, you get more complex loading. You get combinations of these. These are things like bending, torsion, and in general, combined loads. You can combine these together. And the complexity of the loading reflects the number, direction, and location of the external forces and the shape of the object itself. So the various shapes of it, the shape of various objects affects how they get loaded. So a bending load, a very common form of load, is a bending load, like this. This is a non-axial load. Here's a bending load on something that's more bendy. There is both tension and compression in a bending load. There's both tension and compression produced at the analysis plane from 3 or more forces, creating force couples at opposite ends of the object. This tends to rotate the ends of the body in opposite directions of the analysis plane, and they cause the body to deform by bending, curving. One side is squeezed, the other is stretched. So when something is bent, like when I'm bending this ruler, I'm applying 4 forces to this. The lower part that's bending in, that side is compressed. The upper part is stretched. So like in a curve, the outside of the curve gets stretched, the inside of the curve gets compressed. And it barely happens on this, but it's a significant effect on the ruler. And the amount of stretch and compression required to form the bend depends on basically the thickness of the material. So I can bend this very easily in this direction, where it's very thin, but it is hard to bend where it is thick in the other direction. And I can sort of bend this ruler where it is thin, and I cannot at all in the thicker direction. So here we have a pencil, a bending load on a pencil. Now 2 forces down on the ends, 2 forces up in the center. And what you get is you get a force of tension on top and compression on the bottom. And so you have the stress varies through the pencil. You have tensile stress on top and compressive stress on the bottom, and the whole thing has a torque. You know, it's trying to rotate around this slice. Now, the depth or the thickness affects the bending strength. So these beams, you know, this very wide beam and this wide beam here are going to have much stronger bending strength in that direction than a thinner beam would. So the depth, how thick they are, affects the bending strength, because you have to compress the actual bending. You get more stress that is has to do with how it resists the forces. It distributes the force better, and the stress is less, basically. And here are some various bending loads. You could have something anchored on both ends and compressed with a force in the middle. You can have something anchored on the sides with a force in the middle, how it bends. You can have something held stable at one end and bent down, held stable at both ends and bent down, which held fixed here and supported on the other, which gives you sort of weird bend. that help fix on one end and loosely here. These are some various types of bending loads. And throughout the body, you have various bending loads. So for example, in a femur, you have a bending load from the applied force at the ball joint. And so you have tension on top here and compression on the bottom here. And here in the planted foot, you have two pivot points near the ends and a force in the middle. So the bending load will bend it down like that. Opposite the direction of the arch of your foot, basically. Now, another form of non-axial load or combined load is torsion or twisting. When you twist something, you generate shear stresses parallel to the analysis plane throughout the object you're twisting. So you get shear stresses that are, instead of like, they're going around in a circle. They're curled around instead of being just in a straight line. So shear stress will act parallel to the analysis plane as a result of the opposing torques that are applied along the long axis of a body. Torsion causes the body to deform by twisting. Yeah. Twisting. This is not very strong, resisting shear forces, so it twists. And the shear stress from torsion load increases with greater distance from the axis. The tubular and hollow cross-section of bones helps resist torsion because it's strongest around the outside where the load is. So here is torsion. You're twisting in opposite directions at each end of a pencil. So there's an internal torque, and the stress goes around in a circle like that, the shear stress. And it gets bigger as you move out. But the diameter affects your ability to withstand torsion. Larger diameter can help resist torsion because it spreads it out more. It distributes that force, that torque out. So skinny things twist more easily than big fat things. So now human bones are under like quite complex loading from gravity, tendons, ligaments, other bones, various contact forces. So the sustained loading of a human bone is a combination of tension, compression, simple shear loads, bending, and torsion. Whole bunch of stuff. So here's an example with the femur. So there's an axial load from the stress, but there's also a bending effect from this force that's applied off center. So there's a stress due to the axial load, there's a stress due to the bending load, and the combined stress looks something like this. So for combined loading, you basically just add up the stresses from the various sorts of loads involved. I'm not going to have you do any detailed calculations. Cover a little more. Now, strain, we talked about stresses, various types of stresses on the body. Strain quantifies how a material will deform. So when we apply a stress, it causes a strain. Linear strain is change in an object's length. This is produced by tensile or compressive stress. And shear strain is change in the orientations of an object's molecules. This is that sort of sliding motion you get from shear forces, the skewing from shear forces. So linear strain is deformation produced by tensile or compressive stress. It's tied to change in length. It's reported in absolute terms by describing the change in length. Yeah, the intervertebral disc compressed by 2 millimeters. But in general, you're interested in the relative strain. And the formulas use the relative effect. So it's reported in relative terms as a proportion of the length change. Because then you can talk about it as sort of as a property of the material under that stress. And so it's the deformed length minus the undeformed length. So length deformed minus length undeformed over length undeformed. So this is strain. It's written with an epsilon. It's length over length naught. Length minus length naught over length naught. Or you can think of it as the change in length over the initial length. It's dimensionless because this is a ratio of length over length. And it's sometimes reported as a percentage. And that's just the strain value times 100. And it can be more than 100%. Well, potential. Compression can't be more than 100% because there's something very weird inside. Your change in length is longer than your initial length when you're getting shorter. You don't have anything, negative length. But for tension, there's definitely materials that can stretch to twice their length or 3 times their length or whatever. Yes. So if there's something going into a black hole, you're going to have an enormous stress because you have variation in force along the object from gravity. Because the gravitational force is big enough and changes with distance from the object, so that there's, it's significantly stronger on the side closer to the object than the side further from the object. That is going to create, more force on one side than the other, which creates an internal stress. And then it's going to deform, it's going to stretch, it's going to cause tension, and that will cause strain, causing it to stretch until it fails and it tears apart. In practice, stuff falling into a black hole generally gets torn apart and reduced to basically a gas. Depending on the size of the black hole, but yeah, so the tidal forces will overcome the internal strength of the material, and it'll fail apart in general. In theory, if your black hole is big enough and your material is strong enough, you can fall, you can pass the event horizon without undergoing big enough tidal forces to tear you apart. But it depends on how big the black hole is, because tidal forces are a function of how far you are from the object compared to the size of U.
What makes one of the bigger smaller?
The mass.
Like,
So the more mass a black hole is, the further out the event horizon, the point of no return is, where light can't escape. And it turns out, if a black hole is massive enough, the tidal forces at the event horizon, the variation in gravity won't be big enough to really do a lot of damage to you. You're still not getting out. Yeah, and then you'd be inside a black hole and no one knows what happens after that point. I mean, in theory, if it was just there was a singularity, eventually the tidal forces would get strong enough to tear you apart. Because eventually you get close enough to the singularity for the variation to be big enough. But it's just sort of once you get into a black hole, you're literally separated from the rest of the universe, and we don't know what happens inside black holes because of that.
when I said what makes them bigger or smaller, but like what creates a black hole? Is it
They
like-
start as a, well,
Is it like a supernova? Like
yeah, so after a supernova, if the center, the core of a star is big enough, it will keep collapsing, and the forces that would keep it from collapsing won't be strong enough, and it'll just keep collapsing until it becomes a black hole. That's how you get stellar black holes. There are also supermassive black holes. We don't really know how they're formed. Those are the things in the centers of galaxies. And that's the size where you get really big ones for if you're going to not be torn apart like tidal forces. Tidal forces are actually stronger not close to a small black hole than a big black hole, because you end up closer to the black hole, so the variation in gravitational force is bigger. Yes.
oh,
Yes. Well, let's say you had a little black hole, and the Earth. In theory, what would happen is you just fall through the Earth, make a hole, get bigger as it fell through, and if, I mean, it could in theory just eventually settle in the center of the Earth and make, I don't know, it's hard to say. The other thing is that very small black holes theoretically will evaporate. That complicated, but black holes can, consume material from an object that is physically larger. That happens all the time. Because one of the ways we find black holes is they were a binary star system. One of them turned into a black hole, and material from the partner is being drawn into the black hole. So that's a thing. I mean, it's not like it's a cosmic vacuum cleaner. It's just another gravitational object. Like stuff will orbit around it and fall in. If it was really tiny and hit the Earth, very weird things would happen. But like, mostly it would, if it was going really fast and it hit the Earth, it would drill a hole through the Earth and just keep going, because it wouldn't be stopped by the Earth's gravity. But if it wasn't going fast enough to escape the Earth's gravity, then some weird things can happen, right? It wouldn't be. It would be very destructive. Yeah. But yes, what would happen for a material that gets there? The stress gets high enough that the strain gets big enough, when you get a point where you go past the limits of the material and it breaks. Which, we hit the material strength. We'll get to that. But yes, usually when we talk about strain, we're interested in this ratio. So here, if you have a sample of biological material, it's loaded into a material testing machine. The material starts out 2 centimeters long. A 6,000 Newton tensile force is applied to it. And it stretches to a length of 2.00004 centimeters as a result of this force. So what's the strain in this specimen? So the strain is going to be delta length over length. So 2.0004 centimeters minus 2 centimeters over 2 centimeters. 0.004 centimeters over 2 centimeters, which is 0.0002. And that doesn't have units, it's just a number. Because it's a ratio. And well, in theory, things can stretch a lot. In practice, generally, strains are going to be small. Usually, they're going to be quite a bit less than 1. Because most biological material just isn't that stretchy. Now, shear strain is reported as a change in the angle of a perpendicular plane. Shear strain is delta theta. It's reported in units of radians. So it's about the angle change in radians. It's not really even a formula for that. Just, you know, what happened. The plane started like this, and now because of the shear, it's tilted. How much did it rotate by? It's still a ratio, radians. It's arc length over initial length. That's how shear straightens. So here, the shear is this angle, the change in angle here, which would probably end up being this small angle. So it's the change in theta, because you went from 90 degrees to this small angle. Now, Poisson's ratio is the width of an object will also change as it lengthens or shortens. So when you stretch something, it gets skinnier. When you squish something and shorten it, it gets fatter. This is Poisson's ratio. So when an object lengthens, the object gets narrower. When an object shortens, the object gets wider. And Poisson's ratio is axial strain over transverse strain. It's the ratio of how much the object compresses to how much it gets wider. And it's typically, it ranges from about 0.5 and it's typically about 0.25 to 0.35. So if it gets shorter by, I don't know, 10%, it'll get wider by 2.5. That kind of idea. Now, the stress-strain relationship describes how a material behaves under load. And there's two common types of behavior. There's elastic behavior, where something stretches, and then when you remove the load, it returns back to where it was. And then there's plastic behavior, when something deforms and does not return. And that is where the term plastic comes from. Because plastic is generally something, most of these are thermoplastics. They become plastic and deformable when hot, and you can mold it. So the material deforms, but it doesn't return to its original length. This is a permanent deformation, the disruption of the internal structure. You can see both of these in like a paper. Okay, the foot bounces back, you stretch it too far, it permanently bends. That's, elastic until it's plastic. That's generally what happens with most materials. So here is a rubber band. If you look at force over elongation, it's a straight line. You increase the force, it gets more stretch, and that can be expressed as a function of the material by looking at stress over strain. So stress, we divide the force by the cross-sectional area, and strain, we divide the amount that it stretches in length by the original one. And we compare those two. But it turns out for most materials, there is a stress over strain relationship that's a property of the material. And you can use that to figure out, how things are going to act. So if you have something that is acting in an elastic manner, it has elastic behavior, the stress over strain behavior will generally be linear, straight like this. And the slope of that curve is called the elastic modulus, or Young's modulus. And that is the change in stress over the change in strain, or, the stress strain. It's the slope. This is also called Young's modulus. And there's a bulk modulus, which describes compressive loading. There's the shear modulus, which describes shear loading. Materials will generally have different moduluses for tension, compression, and shear. A stiff material has a large E, or elastic modulus. It has less strain per unit of stretch. So it doesn't move as much for the same amount of force. Well, a pliant material has more strain per unit of stress. It extends more for a unit of force. So for example, bone is stiffer than ligaments or tendons. Tendons and ligaments are more pliant than bone. Pliant is the opposite of stiff. So here, this is a stiff material. You can see the slope is steep. You get lots of, it takes lots of stress to get a given strain. Pliant, it doesn't take nearly as much stress to get a given strain. We will do these problems next time. I just want to go a little bit further. The other thing is the plastic behavior is when you reach the limit. The elastic limit is the point, the yield point for a material on the stress strain curve. And stress above this point causes a permanent deformation of the material. And if you look at a stress strain curve, what you'll see is it stops being straight. And the material doesn't return to the original shape. And the mechanical strength of a material is the maximum stress a material can withstand before it fails. So here, the yield point, where it goes from being elastic to plastic, is here. And the strength is the maximum stress, the maximum height you get. That's the mechanical strength. And you can talk about different strengths as different points on this. For this particular material, it will yield, it will deform plastically, and then it breaks. The yield strength is the stress at the elastic limit. The ultimate strength is the maximum stress it can withstand. This is where it starts to give way, and the failure stress is where total failure strength is where total failure occurs. And sometimes the failure strength can be less than the ultimate strength because it'll go up to the ultimate strength and then lower down as it deforms. So yield strength, ultimate strength, failure strength. And I think that's where I'll stop today, and I'll go over this all again on Thursday. Any other questions? Yes. Not always. You can stop. So the ultimate point of failure is when it reaches a certain amount of strain. So you could get it up to the ultimate strength and then stop. And if you unloaded properly, you could get back down into a safe place, but it wouldn't be a great place to be. Because you permanently deform that thing. And you could get a situation, yeah, you could end up on this side. It's not a great place to be. But it doesn't necessarily always lead to failure. But yeah. And this gets really common. Okay, so that one, right? Just hold that down. Oh. It'll be recorded in Zoom. Mhm. So I'm gonna